So AT&T had a conference, right, at their office down in El Segundo. And they had H2O there.
Oh,
yeah,
the toolbox.
Toolbox,
yeah.
And then they had R Cloud. Weird. I mean, kind of, but they had like.
Well, R runs into problems with like big data.
Yeah.
Like it's not really made for that. But
yeah, it was just good to listen to them.
Yeah.
In here.
But I guess that's what they're
well,
doing.
Yeah, the R Cloud
yeah.
will allow you to get the big data sets. Exactly.
I have not heard of it, but like.
Oh really?
But it makes sense.
Okay. Yeah.
Okay. So I hope you found the scikit-learn tutorial useful, and now all equipped with what you need to run your own experiments. I'm going to try to post a homework today. I'm going to get some feedback from Lishing to exactly know what we're going to propose. But I think mainly the plan is for you to get like a standardized data set, and I would like just to see that we can basically, you can freely choose your classifier, but then we'll like have you go through the different paradigms of classification experiments, so that like we have all the tools to run the class project. So you know, like some validation, some held out test sets, and so on. So it's like just I want to see that you know what I meant with that, and then I would like to see some evaluation metrics, and you can come up with some, and I will like define a few. I'll say like classification, I would say, because the data set's going to be balanced, so you don't have problems with like F1 score. So accuracy is nice. Confusion matrix would be nice to see, but I'll define that. And yeah, so I think that would be kind of like a nice exercise. We then had a discussion about like data handling. We walked through this, like how to deal with different types of data and different types of scaled data, so like ordinal, nominal, continuously scaled data. And I think we went through a couple of useful descriptions and ways to describe what's in the data set or what's in your data. And I think for your course project, I think these metrics are quite useful to like just familiarize yourself with, just to get a better understanding of like what is likely going to work when you do your experiments. Like just get a feel for the data. And often your data set is so like large that just looking at every single data point would not be feasible, and that starts at like 100 data points, right? So these descriptive statistics and like visualizations that we discussed are really useful to get a better sense for what's going on. And so one of the things, for example, also, if you have a means to like estimate the distribution, the PDF function, the distribution function, probability distribution function for your data set, I think it would be also nice to just like, for example, plot one of these curves for like one class and the other curve for the other class, so you could see like how likely this feature would be able to discriminate between the two. So that's quite useful as well. So you don't have to just plot one, but you can plot multiple ones onto a plot like that. Alright, so we discussed like how correlation is also interesting. However, again, like correlation only captures linear dependencies, but not more complex dependencies that you could, for example, capture with like some clustering methods or something like that. Okay. We walked through a couple of graphical representations, and I think the concept here is like there are different types of graphical representations that can be interesting at different points. So the histogram obviously is like a approximation of the actual probability density function, and bar plots, for example, are quite interesting as well. Like they give you mean values, but they don't like add more information than that. So you don't know where the data points are distributed around this mean value. And you can imagine, for example, I mean, if this is bounded by a 0, obviously there's going to be a lot of like compact representations or like compact observations down here. But if it's like more wider than this, as this, like you don't really know what the variance is of this data set. And for that purpose, these box plots are more useful and give you better insight. They're also more compact, and you can measure basically the compactness of a visualization by, you know, for example, like the number of data points per square inch or something like that. Yeah. So like if you think about this as like these are just the data points here, you don't have more than these 6 data points, but here you have many more. You have, first of all, you have 6 mean values, you have 6 respectively for the upper and the lower quartile, you have these outliers and so on. So you have like a lot more information in these plots. Then we talked about the scatter plots, and that scatter plots can be nice to visualize your data with like maybe a regression line in there, so that gives you like a nice understanding of the dependency between 2 random variables. Yeah. Further, we talked about like, yeah, find further like what box plots look like. So basically this is like how you can imagine the box plot is represented. And all functions like NumPy, I think, or yeah, I don't know which ones, oh, no, PyPlotlib or something like that is the plotting library for Python.
Mm-hmm.
They have all these functions, so you just give it the data points and say like boxplot or something. They might have a different name for it, but if you go through the tutorials, they should cover these basic plots for sure. And we briefly said that obviously that there are other visualization techniques that might serve a different kind of purpose, and I think you can basically identify for yourself if you want to maybe use different visualizations with obviously like varying degrees of effort. These I don't think you would have like direct availability in PyPlot or whatever. I think this, like these word clouds, you can easily get, but others might not be as easy. Okay, so any questions for that? I think should be fine, right? All right. So let's continue to the next topic. Basically, this should give you like a basic understanding for what is underlying machine learning, like in probability and Bayesian decision theory, and like what the decisions are, or like how you can basically break down a classification algorithm to like a probabilistic model. And we're gonna walk through a couple of the basic classifiers with this theory in mind. So we're gonna talk about nonparametric classification through, for example, k-nearest neighbor, which basically just estimate the density of certain classes around a new data point that comes in, and based off of the density of the support that the other class is providing, you make a decision, oh, it's this class or that class. The one that has a higher density gets to be the winner. We're going to talk about naive Bayes, how you can do, for example, document classification with naive Bayes. We're going to go through an example there, and we're also going to talk about like different types of penalties, like loss and risk, and how you can assess, like based off of like probabilistic theory, which choice to make. What is the cost of my choice, and how can I minimize my costs? Okay, but that should become more clear in a second. So first I would like to start with the idea of observable versus non-observable variables. So an observable variable is something that you see in your data set, and an unobservable variable is something that influences your data set but you don't know about. Okay, so weather forecast, for example, you have a couple of temperature, wind, humidity, etc. You have these observable variables, but then you have butterflies in China that or like a rice sack that falls over and influences the weather. Like, obviously that's not really true, but there are unobservable variables that you don't really have access to. Like weather stations are not at every location on the planet, but they're at like certain locations and so on. So you don't have all the information, but you have a good approximation of the data. So so data usually comes from a process that is not completely known. And some of your unobservable variables could also be noise, right? Like you don't really have full-on access to like how well your sensors work. Your sensor might not be completely accurate. So the model that basically draws your data is a random process, and we try to analyze it with probability theory. So an example is like if we toss a coin, this is a random process, but we cannot predict what side the coin will fall on, and we just have to like choose the one that we believe is more likely, right? So if we believe that heads is more likely than tails, we should always say tails. No, heads, obviously. We can basically only talk about the probability of the outcome, so the observable variable for the next toss. We don't know everything. However, obviously, like if in case we had all the information, the velocity, the rotation angle, the wind, etc., we might be able to predict the outcome precisely, but like most of the time, we do not have access to this. So what we need to do is we need to choose the outcome that we think is most likely or most probable, okay? So let's define this further. As a random variable, we define the outcome x as we define the outcome x, so heads or tail, as a random variable. We draw from this probability distribution, and p of x equals small x. In this case, could be 1 or 0, heads or tails. Specifies that process. And then p0 or p tails is the probability that outcome is heads or tails, and then the other one is 1 minus p0, okay? And then basically, if we know p0, in this simple example, we choose the one that's more likely as the outcome, okay? So if p0 is greater than 0.5 because we have 2 classes, well then we choose p0. If we have multiple classes, we choose the maximum, right, of p1 or p0 through k or something like that, okay? If we have k classes or k plus 1 classes in that case. So we choose the most probable, and basically that gives us the ability to have the least error. So we reduce our error, or we reduce our risk to make a mistake, okay? So that should be fairly clear. All right, so, and most of the time, as I said, we don't have access to this probability distribution, and we can only like basically estimate it or estimate it based off of a sample. So our sample then is basically denoted as small p of x, and we only know how many times, if we do like look at our data set, it happens to be tails or heads, okay? And basically we can estimate this, like we usually denote those estimations with a hat. So p0 hat is the number of tosses that come out as heads divided by the number of tosses. So let's say we have 10 tosses and 6 of them or 9 of them are heads. Well, p0 is very high for heads, so we should probably think that this coin is rigged and that likely we should just always predict heads. Okay, so if it's a completely fair coin, it should probably be somewhere around 0.5, and really don't really know what the outcome will always be. And here's obviously an example. So in this case, we have all these observations, and we know the outcomes, and we can basically say, okay, this is how so p0 hat is 6 divided by 9. So if this is larger than 0.5, so we should probably choose heads for the next toss, okay? And this is if we have everything, we have the observations and we have the labels, right? So we can estimate the probability for heads or tails, but often in machine learning, for example, we do not know the estimates and we do not know the labels, so like that's where, for example, expectation maximization comes in, where we would try to fit our distribution like through an iterative process rather than computing it directly, but that's not really what we need to do here, okay? So, is this fairly clear? So basically, you have a sample, your data set, you look at how many times you observed something or an outcome, and you divide it by the number of times you, or like the number of samples you have here in your data set, and then you identify, okay, which one's more likely, which one's less likely, and that's the one you're going to predict because that's the way you minimize your risk, okay? So this is really not very much like machine learning right now, right? But it's a basis for that. Okay, so if we go back to our family car classification problem, we basically now have two observable random variables. We have price and power, okay? So we just represent those as two random variables, x1 and x2, and what we need to really find out is, so in heads and tails, both the observation and the class is the same, right? In this case, we have two observable variables, but the class is something else, okay? So what we need to really estimate is the probability for observing a family car or no family car, we have two classes, given our two observations, okay? So we need to compute this probability. All right, and that's not very easy. Let's get that right out of the way. Oftentimes this is actually problematic to do because we don't really have the ability to get at that probability directly. So yeah, so C equals 1 if it's a family car and C equals 0 if it's not. So we can come up with a rule though and say, well, we choose if it's C1 if the probability of C equals 1 given an observation is greater than 0.5, okay? We can also say, well, we don't really have to like use 0.5 as a threshold here. We can also just say if this one is larger than that one, okay? Or we can say if we have multiple classes, the max of k, and we choose k as the class, okay? And otherwise, we use another one. Okay, so like if you have a maximum in here, you can just write that in one line, and so on, okay? So, basically, and here, like for the error that we would estimate here, is in this case, the maximum of those two, with like 1 minus the maximum of those two. So, so if we're, for example, not 100% sure that it's going to be a family car, but we're only like 70% or like 0.7 probability kind of sure that it's going to be a family car, well, the error that we're going to make is probably like something around 0.3, right? Yeah, so the problem, however, is in most cases to actually calculate this. And does anybody know how we can get around this problem to calculate this probability there, which is called the posterior probability? So, Bayes rule, exactly. So it makes it, we rearrange our probabilities so that we don't have to compute the posterior, but the prior likelihood and evidence. And so we can rewrite this posterior probability as P of C. That's the prior probability. So that's basically, in my sample, I have like 5,000 observations, and 3,000 of those are family cars. So my prior for family car is 3,000 by 5,000. Okay. And then we have my likelihood, which is basically the probability of observing X given that it was C. And that we can learn from our data set, right? We know the labels, and we have our observations, and we can see, okay, how many times do I observe this number, or this price range, or this power for a family car, when I have the class C as family car or no family car, okay? And then we divide this by P of X, which is basically the evidence or the likelihood to observe the given variables, okay? The interesting or the cool thing, if you want to do, for example, classification with this rule, so P of so like the class equals 1 or 0 given X can be written as this, right? But like the probability of X is independent of C, so if you want to do classification, you don't really need to compute this, right? But if you want to actually have the probability and to like estimate it correctly as a likelihood variable, you need to compute it. But if you just want to make a decision, yes or no, you don't actually need to compute that P of X, okay? The evidence is only needed if you want to actually model the distribution. Okay. So, okay, this summarizes this. So obviously, like, okay, it's known as P C equals 1 is the prior probability, and then we have the likelihood, which is the conditional probability that an event belonging to C has the observation X. And as I said, we can get that from our data set. And then the evidence is the marginal probability that observation X is seen. So it's basically, if you want to formulate that, you know, in a binary class problem, you can write that as such, okay? And you can, again, get that from this part here, right? Okay. If we generalize this, we can generalize this to like k many classes. Basically, prior probabilities satisfy the following, that at least the probability for a class I out of these k's must at least be like 0 or greater, so it's non-negative. And if we sum those priors up, we have 1, right? So because we need to observe something. And then the posterior probability of class Ci now is calculated as such. So we set in Ci here, we just replace C with Ci, and this again, as you can see, stays the same for all of them because there's no Ci dependency in this one, and you need to compute this over all the classes, okay? And then basically the Bayesian classifier is choose Ci if PCI is the maximum of all the classes, okay? So that's what we have to do. And so that, like, to move this kind of like out of the theoretical world, we could do an example, and we're going to walk through an example, and we add a little additional simplification for this example, and we'll introduce the naive Bayes classifier. So the Bayes classifier basically just wants to do this, right? But the naive Bayes classifier has a little bit of an extra simplification in there, which is basically an assumption over our observations. So to introduce what we're going to do, we're doing text classification. So we want to know in your email box, you go through all your emails, and based off of what words we observe in your email, we decide if this email is spam or ham in that sense, or like an actual email or a spam email, okay? And what the features that we're going to use are basically bag of words, so it's just a vector, so it has the length of the vocabulary, so we have to decide like how many words do we allow, like how many words do we want to look at. We can say maybe for English we would say let's do the 100,000 most frequent words in English language, right? And then if you think about this, okay, so you have 100,000 words, that already starts to become a little bit tricky because the spam email bots have learned kind of like about this, and so they, I don't know if you're old enough to know that like they started to like replace some like letters with symbols, and now these words kind of fall out of vocabulary, doesn't really know what to do with those, and so on. And like if you just change those patterns over and over and over again, it's really hard for the algorithm to actually like always be on top of that. So it needs some learning mechanism, but we ignore that for now. So we only have like proper text messages. All right, and the important part of this is also like the bag of words is not ordered. Doesn't like have an order of like this is the first word, this is the last word. It basically just is a vector, and each column represents a word in the vocabulary. Okay. And then we have like a collection of emails that are marked as spam or not spam. We want to learn from that. Training data comes from wherever. So this kind of like, it could be from your inbox and you labeled them as junk or no junk, and so on. Okay? Alright, so, and this is just a little bit of additional information. There's actually a lot more than spam filtering. There's the sentiment analysis, for example, in the effective computing community, where you would like to classify reviews for movies, if they're positive or negative reviews, and so on. Like they could be also in sentiment, could be positive, neutral, negative emails or whatever. And then, yeah, you can assign topic categories because it makes it more interesting to like browse or something like that. So you have like sports, politics, and so on. All right. So, as I said, the naive Bayes classifier does an additional assumption, and that basically can be represented in this graph where each of the words is independent from each other. Okay, so you are not like looking at words together, or like all the observations in your classifier are independent from each other. So like this observation here does not influence that one, and obviously like in written language that is not necessarily the case, but it's a simplification that makes it a lot easier. And it's like used as a pretty common baseline, and it can do surprisingly well often. Like, so you could, for example, if you have like a text classification problem, you want to know right off the bat like how quickly or how good your features might be. You just do a naive Bayes, and like the output will be fairly quickly. And so you will know like what a good baseline is for your task. People use it for all like sorts of classification problems, and what we want to do is we want to know the probability of spam given our words that we observe. Okay, so naive Bayes is set up as follows. So, like, suppose we want to know if an article is about sports. The classes are these, like sports, politics, entertainment, and the probability of a document that belongs to D. Document D belongs to class C is the probability of class C given document D. So this is kind of just like reiterating how we reformulate from probability of class given document equals probability of class, so it's a prior document given class, and divide by the evidence. Okay, and then just for your reference, well, we choose the one that's most likely, and we want to find class C star, and we do this with this probability, and you can see we don't divide by PD anymore because we can simplify it that way. We don't really need to know the actual distribution. So how do we estimate PC? So the probability of class C. We had said that this is called the prior, right? So we know the prior right off the bat. We just look at our data. We count how many lines are spam, how many lines or in my data set are not spam, and we basically just say, okay, it's like the number of lines for one class divided by the total number of lines. So that's easy to do. And then, but how do we estimate the probability of document D given C? And so document means many words, right? And we said that all the words are independent. So what we can do is we can simplify this into like P D given C equals P of word 1 given C, P of word 2 given C, P of, and so we just multiply those, okay? That is the naive Bayes assumption, where basically each word in the document is treated as separate, okay? All right, and we can get those fairly easily by just counting in our data set, right? So we know how many times the word just happens to be like close or like labeled with the class, okay? So let's look at our data set. It's a fairly simple data set. We have 3 spam observations and 3, 4, 5 non-spam observations. And well, the spam one, for example, reads click for pharmacy, online pharmacy link, pharmacy free link. So there's something about pharmacies and links that might be like related to spam, right? But there's also pharmacy happening here. There are no links in the OK ones, so maybe that's just a coincidence. There's a lot of time, so maybe like we get a lot of like meeting notifications from colleagues and so on. Okay, so what's the vocabulary size? That's basically the length of our input bag of words vector. Does anybody know? Well, you would just start counting all the unique words, right? Yeah. And I'm not going to let you do it. It's 12. Okay? So these are just all the unique words. All right. What's the prior for spam? 3 over 8. Yes. Okay. That's basically our maximum likelihood estimate. We don't really know what it is, but we estimate it. Alright, so for not spam, it's 5 over 8, right? So that's easy. Okay, so here's a trick question, or like an interesting one. Like, what's the probability for pharmacy given spam and pharmacy given not spam? So we have pharmacy here, here, and here, right? And it's spam, spam, and spam. Okay? So what is the probability for that? That's pretty easy, right? Like for pharmacy given not spam.
1 over 4.
So it's not happening in any of the okay.
Mm-hmm.
So that one's. Oh, there's one. Wait. Oh, yeah, there is one. Ah, yeah. Okay.
Pretty good, probably.
1 over 5 or 1 over 4.
Is it 1
4?
over
Why 4?
Because there's 4 pharmacy words.
It was 1, 2, 3, 4, or 5.
Yeah, no, that's not.
Oh, that's fine. That's right.
3, 4.
That's not how this works. Okay.
Yeah.
And so what is the probability for pharmacy given spam?
3 over 4.
Okay. So yeah, that's not how you calculate that. So what you do is you look at, like, if you have spam, how likely is spam to generate the word pharmacy? Okay, not the other way around kind of thing.
Yeah.
Okay, so we have 3 observations where pharmacy is happening in spam. And so what's the likelihood that generator spam generates the word pharmacy?
1. Based on this set, it's 1.
It's so if it was 1, what word would the documents look like? It's pharmacy. Like that would be the document if it was 1.
It would be 3 over 6 because there are 6 unique words in spam.
Okay, so so spam produces 6 different words, but it also produces 1, 2, 3, 4, 5, 6, 7, 8, 9 words. So it's 3 over 9. Like so, it's a third. Like every third word is pharmacy. Okay. And then for not pharmacy, not spam, I think it's 15 words because like we have 5 and every document has 3 words. So it's 1/15. Okay. So basically, it's about like the likelihood that spam produces one of these words. It's kind of like a generative model. Okay. All right. So if we have those 4 numbers now, we should be able to calculate this. So this is again like the posterior, right? So we know we want to know the probability of spam given a message. How do we do that? Well, first of all, we apply Bayes' rule, and so we get the following. We get the prior for spam, which we have here. The probability for message given spam. Well, we have words given spam, and then we decided that we do naive Bayes and assume that every word is independent of each other. So we would just put in the different words and multiply. Okay, and then we have the evidence that we said, like, if we just want to do classification, we don't really need to compute that, but if we want to like actually know this probability, we need to do that. So we just have the same thing here, right? And then we just do the opposite with no spam. Okay. So message given spam, as we said, we can now represent as such, right? So every word is independent. For the first one, for example, we do click for pharmacy, okay? And then we have a new message though, so it's pharmacy for pharmacy. What would that be? So P word 1 given spam. So pharmacy goes in here. We have that one, that's a third, so it's a third times 4, which is happening once, so it's 1 out of 9, so 1 over 9, and then pharmacy again, so it's a third again, okay? And then 3/8, we had that from the prior. We basically have following now, okay? And then we said this is the same as that. We can replace that, so it's both are 2 divided by 216. And then we need to compute this. And that's pharmacy happens like 1/15th, so it's first 5 divided by 8 times 1/15th. 4 is 1/15th, and then I got another one 1/15th, okay? So that's basically pretty small, becomes this. I hope, I'm not sure if I did that correct. But anyways, like if you then compute like the values here, you basically get to the following, that the probability of spam given the message is 0.96. And so what we would do is
Label it as spam.
exactly. All right. And then we have a new message, time for pharmacy. Okay. So now we need to compute this, and obviously this is kind of like a special case. Otherwise we wouldn't do this. But so if we need to compute this now for this message, time for pharmacy, we run into a problem because we multiply the probabilities here all the time, right? And then if we look for time in the spam category, it's 0. So that means that is 0. The whole thing up here is 0, then this is 0, and well, 0 divided by something. So we have a problem, right? The problem is we would never be able to do this, and that classification is obviously bad. We just haven't observed this for our spam data set. And a possible solution to this problem is if you just add every word in your vocabulary if it doesn't ever happen to be in the class. You just add it once into your span class. So it would be just the smallest probability instead of 0, or you just do epsilon instead. So just that you have this to be like not a 0 there, right? So and that one basically is called add-one smoothing. So when you just add every word at least once into your classifier, into your sample set. Okay, does that make sense? All right, it's pretty practical, and like this is kind of like what's happening, and you know, it should be fairly easy to kind of also build a classifier like that, like in Python or something, and we might do that as a homework or something. But that's basically like how naive Bayes works, and you just calculate a bunch of probabilities, you reformulate them, and make it easier for yourself. Okay. All right. I think it's a good time for a break. We can just come back here at 10:55 and continue from there.